All right, let's begin. Welcome back. After the break, you had 2 weeks break. I hope you enjoyed your break time. And then everyone should have their quiz 1 and assignment 1 mark by now. If you haven't got it, let me know. I hope you got it. And if you got any issues with marking, let me know as well. Have you got your marks for A1 and quiz 1? No, yes? Okay, good. Okay, now you are in the second half of your course, and then I believe you started with chapter 5, which is limits of sequences and series, and all those things. How far have you covered? Let me check the course reader. Yeah. So we are in week 7. You got your assignment 2 already on the course website. Did you have a look at it? And it's like due after 3 weeks by the end of this month. So we got a lot of time, like 2 weeks before that, where I can help you with the assignment. Okay, I believe you have covered some part of in the lecture about limits, computing limits of sequences and series. Is that so? Yeah. All right. Now, the plan for today is, if you look at your assignment, so Tim has asked me to discuss the bisection method, which is how to implement bisection method, bisection method in Mathematica. Now, in this tutorial, I'd like to go through an example of bisection method, which is very easy to understand and clearly explained by Sam Hamilton, Dr. Sam Hamilton. I would like to share the video of the example because it really explains the step by step. I have the code with me, but it's really helpful to understand the steps. Okay, let's look at the theory behind bisection method. Okay. Okay, before that, I'd like to share the notebook. Please note that this notebook I will update as we go along with these 3 weeks. So please be aware that this is not a complete notebook yet. I will update this notebook towards the beginning of the next week as well, and all the codes and examples. So if you got any question on the notebook coding, let me know on Piazza. Okay. Okay, let's look at the bisection, the theory behind bisection example. Okay, you probably, some of you may already know this, but let me go through the basics. Bisection method is a root finding method. There are many root finding algorithms, but bisection method is a well-known and a robust method. Um, uh, in it, you need to have a real a valued function which is continuous, and you need to know two values with opposite signs. Okay, for example, let's say um, that's y x. Okay, maybe your function is something like this. Okay, um, it is continuous, it's real valued. So we just want, that's f of x. We want to find all solutions of the equation f of x equals 0, okay, using the bisection method. The idea behind bisection method is you would need to have 2 points where the function is, let's say, if I have, let's say a and b. Okay, at one point the function value is f of a is negative, and the other point the function value of b is positive. Okay, so you need to have an interval, start an interval like this, and then ideally what it does is it takes it bisects the interval, continuously bisects the interval as it moves along. That's okay. Take the half of this interval, and then as it move along this line, okay, it is an approximate, it gives an approximate solution um, to the function. Okay, now for simple functions you can compute the solution easily, but for quite complex functions you might need to approximate it. Okay, so it's, the idea is continuously bisecting, dividing the interval into half, and then move along the curve to reach to a point where there is a approximate solution. Okay, now there are some conditions that you need to meet in this. So the application of bisection method is to find a numeric solution, which I already explained, where you need to have an interval where you have f of a and f of b have opposite signs. And then this is a robust method which guarantees convergence, because the intermediate value theorem guarantees that there will be at least one root in the open interval a and b. Okay, the method repeatedly divides the interval into half and selects the subintervals in which the function changes sign. Okay, this is an illustration which I already explained. So what happens is it starts with like a1 and b1. That's the interval. For example, that's a hypothetical function. And then when you take a1 plus b1 divided by 2, that gives you a point C. And then you would look at f of c. Okay, and then see whether f of c is close to, whether this is bigger than or equal to 0. If it is bigger than 0, it is more close to f of b. Okay, close to f of b. So then the new interval would be c, b, okay? And like that, it just goes on, okay? If it is less than 0, then the new interval would be a, c, okay? So that's the idea behind the bisection method. Now, the algorithm requires input functions and the first interval and their values. And then at each iteration, it performs these steps, calculates the midpoint, which I just explained, compute f of c, check the conditions for convergence, okay? The conditions for convergence is that the distance between C and A is sufficiently small, or the other condition is the absolute value of the function is sufficiently small. And some algorithms use the absolute value. If it's satisfied, we return C and stop. Or in the next step, we check the sign and replace either the point AFA with CFC and or the other way around. Okay. When implementing this method on computer, you need additional convergence tests to the number of iterations to avoid finite precision. Okay, now one question would be like, this is a slow method. Bisection method is a slow method, which I will discuss later. Yeah. Yeah. Okay. But there are advantages of using the bisection method. Okay. The algorithm, if you want to write your algorithm, it should be something like this. So you input the function f and the endpoint intervals, tolerance value, the maximum iteration, and then find the conditions, either f of a is less than 0 and f of b is bigger than 0, or the other way around. And then output the value which differs from a root of fx0 by less than the tolerance. Okay. The video which I will show you explains very clearly how to implement all these steps in Mathematica. For an example, which is quite complex, when n equals 1, you start with n equals 1 and have a while loop to compute the new midpoint and check the condition. And then after n plus 1, that is the increment the step, if the sign is the same. Okay, okay, different programs implement this differently. If the sign is same, then A equals C, that's the new interval. Okay. Now, now this is what I said. Since f is continuous and the sign of f of a and f of b have opposite signs, there is the convergence is guaranteed by intermediate value theorem. Now let's say the solution is C, then the absolute value of Cn, which is the midpoint of the nth step, is bounded below by B, the absolute value by bounded above by the absolute value of B minus C to the power 2 to the power n. Now, the convergence rate is linear, which is this part can indicate the number of iterations required. All right, which is n should be less than or equal to log to the E0, which is E0 is B minus B minus C actually. Okay. And the epsilon is Cn minus C. Okay. Now the disadvantage of this method is it's a slow method. There are fast methods than the bisection method, which, like for example, Newton method is fast, but it also has problem. Okay, but the advantage of bisection method is a solution is guaranteed. Okay, it can hardly go wrong. All right. For example, okay, let me do a hand calculation example. The first step I will show. Let's say you have this curve here, fx equals x cubed minus x minus 2. I've used Mathematica to plot it. Its shape is like this. And then there is a root between 1 and 2. So let's say the interval is 1 to 2. The starting interval is 1 to 2. Then if you compute f of 1, which is equal to minus 2, and f of f of plus 2 is equal to 2 cubed minus 2 minus 2, which is a 4. Okay, then you would compute the first C. C1 is equal to your interval, that is 2 plus 1 divided by 2, which is 1.5. Okay, now the function value at 1.5, f of C1 is equal to f of 1.5, which is equal to minus 0.125. Okay, this is still negative. So A is replaced with 1.5 for the next iteration. Okay, this is less than 0, so A is replaced with A equals 1.5 in the next iteration. And then you would compute the next interval again. Okay, so now you got 1.5 to 2, and then you would divide the interval and compute it like this. Okay, so that's the idea behind bisection method. Okay, any question regarding that? All right. Implementation of the bisection method in Mathematica is there is a very good explanation. If I go through the same steps, it would be like I would be repeating the same thing. I have the code with me, but I would really like you to watch the video of Sam. He really explains everything so well. Let me check. Okay. In the handout, I've asked you to use implement bisection method for the function shine x minus 3 plus x cubed minus x to the power 4 plus 15 in the interval minus 1, 3 is a sequence of intervals. Okay, now the code is written here. I've got a little bit error in the code, which I will update. Okay, but ideally, the first thing you would want to do is have a plot of the function. Okay, let's see. Oh, I have it here. But anyways, let me do it in a minute. Okay. There appears to be two roots. One is between -1 and 0. The other one is just before, like about 1.5 and then 2.5. Okay, that's a good start. Okay, so always have a look at the function. Plot the function before you start the method, just to see where your A and B intervals are. Okay, and in the first part of the algorithm, I built a function to evaluate fx at a given x value, which is the same step that Sam was explaining in the video. And the other thing that he's done is build a function to output the true value, output true if fx is greater than or equal to 0, and check if this function, like this is just some code where I have checked the function, whether it's true or not. In this part, check the function and find the average of the interval and call it u here. Okay. And if this is the condition that for the bisection method, if this condition, if the first endpoint is, if f of the first endpoint is bigger than 0 and f of the second endpoint is less than 0, then return the midpoint and P2 when f of the midpoint is bigger than or equal to 0. Okay. So that's the idea behind that condition. This is the condition module from that I've used. And then the last one is measure of convergence of the bisection using the absolute value of the distance greater than the tolerance which you will give you. Okay, ideally you want the tolerance to be very small for a good approximation. Okay. Okay, that's really a step-by-step method of implementing that bisection method for this example. But there is a very simple and elegant code which can combine all of the above steps. Okay. I will also give this code to you when I update the notebook. Okay. That's all you really need. Okay. In that code, which was which was explained in step by step. All right. And then after that example, the second example, I've asked you to find the intersection of y equals x and y equals 1 minus x, x to the power 2, x to the power 2 divided by 5. Okay. All right. Okay, let me show you this video so that you can later on refer to it. but I'd like you to go through these steps by yourself and find the solution. Yeah.
All right, now the first thing we want to do is plot this function.
Okay, before I move on to the video, is there any question? Is there any question that you would like to ask? Okay. All right, that's
okay. So this is
as I
rather easy. We just write
could
plot.
you please complete your notebook with the code?
And now this is the hyperbolic sine function. So it's uppercase S, I, N, H. Right? Of course, this involves exponentials. Sine of x minus 3, and then we add x cubed, subtract x to the power of 4, plus 15. Right now, we want to plot this so that we can see where the roots of this function are, or the zeros of the function, right? Because those are what we want to find using the bisection method, right? So let's choose a range to plot this in, or domain. Okay, and shift enter and see what we get. All right, so it looks like we've got at least 2 zeros of the function. Okay, now looks like there's one between -1. Think of a name for it. Let's call it Bob. Okay, so Bob will be a function of x, colon equals module, place for local variables, okay, which we don't need any. All right, now it will just check the sign of Carla, which of course is just f of just AV for average, all right? And we're going to, it will be a function of an interval which will look like a point when we enter it, okay? So it'll have an x and a y component as points.
All right.
And
what I'll do is I'll fast forward this because I've got
right,
all
so
the
that's
coding.
what this one does. And now the one we are constructing is, in this case, returning the average followed by the right-hand end of the interval. And this is our new interval, okay? So it's got half of the width of the original one. All right, now, if that is not satisfied, so, oh, sorry, we want to return this when f of u is greater or equal to 0. Okay, and then, and the other way around, otherwise, as in p1 to u otherwise. Okay, and that is what we want to do in this case, when f of p1 is greater or equal to 0 and f of p2 is negative. All right, now if it's the other way around, okay, so let's say if we do not have, for example. Okay, so lower tolerance and getting closer and closer to an approximation of the root of your function with the bisection method. Okay, next we want to say n equals 1 for where we're starting in our while loop. And we need to enter an interval. Right now we already did p equals PAM of p. Right, so we are putting in p and outputting a new interval that's got half of the width when we need to keep going. All right, and so we'll put in a semicolon, and at the same time we want to see what the output is, so we'll go print p semicolon, and then we'll say how we're incrementing. Right, whoops, don't need the comma there. We'll just say how we're incrementing, so n plus plus. In other words, increment by 1. Okay, now that we've got this, we can press Shift and Enter and see what we get. Okay, so now you have, coming out of this, are a more accurate solution to a 0 of half. And then these down here, which take it has broken the while loop when the tolerance was found. Okay, so let's see if we can decrease the tolerance by including a few more zeros before the 1. Let's copy this.
All right. If you get in your own time, you could view this video, but let's have a look at the coding. Can you try this by yourself, okay? And fill in the notebook. I'll give you a couple of minutes to digest this and then try your own code. If you got any questions, let me know. Are you guys okay with that? Okay, is there any question? Let me do this. I think I found where the error is in the code. Okay, let me do this step by step so that I can catch it. Yeah, here's the error. Is there any question? It's select whether between P2, P1. Oh, okay, that's where the error is. Now it should work. I hope so. No. One, two, three, four. Okay, let me write this. So okay, did you guys get an error here? In this step? I think I missed one bracket in the previous one. All right, I'm still getting the same error, which I will have a look at. Let me check the while loop. While test condition. Okay. Definitely there's something in the while loop which I need to fix, but I will update this. I will have a look at this and then update. Okay. Um, update the notebook on GitHub. All right. But let me share a very simple step program which does everything that was explained in the video. Okay. And I will give this code as well. All right. Is there any quick question? We have got almost up to the time. Is there any question that you would like to ask regarding bisection method? I've got another tute at 10, so I'll have to be quick. If not, let's stop the tutorial for today, and then let's conclude the practical for today, and then see you next week. Okay, with more examples related to the assignment questions. Okay, thanks for attending.